try some more problems like that. Okay? Okay, so you have this one. Find the area between y equals x cubed and x equals y squared minus 2. Oh, it tells us we get to use a calculator for this one. Yay. Okay. So if I'm thinking about this one, x cubed, mine's going to look something like this. Like I've been doing before, I'm trying to color code things. Right, this one I don't love graphing it. It seems really hard for me to graph because I got the y squared and I don't do that very often. But let me try to think of an easy value. If I plug in 0 for the y, that means that x equals negative 2. Okay. If I have x is 0, that means that y is plus or minus the square root of 2. Square root of 2 is about 1.4. Doesn't matter exactly where you are. Remember, we're just trying to get an idea of what this graph looks like. Okay. So it's going to look something like that. Let me just check my work here real quick. Okay, so that looks good. I just wanted to make sure I have my graph right, okay? So if we think about it, if I was going to try to integrate in terms of x, that means my slivers would have to look like this, which is fine right here. It's fine right here. It's fine right here, but it's not fine over here, right, for myself, because you can see that if I made a sliver here, I'd have the same function as the top and the bottom of the bounds, and that's no good. You can't have the same function as your upper and lower bounds. It's really annoying, obnoxious. You don't want to do that. Okay? So, but if I did make my sliver this way, all right, if that's my rectangles, like this, oh, then that thickness there is dy, and right, the height of it's dy, and this is the change in x for myself. And that's always going to have the black function as the upper limit, as the upper bound, and the pink function as the lower. So in this case, it's always going to be, right, the upper minus the lower. Right? And that's always going to be true. So that's nice. We like that because this also tells us that since we have the dy, that means we need to have these equations in terms of y. Right? So that when we set up our integral, because the thickness of this rectangle is dy, we have to make sure these are both in terms of y. Okay? So the upper is the function that's black, and let's see, the function that's black was, right, the y equals x cubed. Wait, that needs to be in terms of y though. So I'm going to make it x equals y to the 1/3. Okay, so that's my upper function. Okay? Just changing that up. Okay, and then this one is going to be my lower function, right? It's already, that's great. We already have it in terms of y. Perfect for myself. Okay, so minus the lower function. Okay. Notice what we had to do for this one. We had to solve for x. It's a change in the x value, so you have to have this equals x. That's why this one was great, that it was already solved for x there, right? And this one wasn't so great because it wasn't solved for x there, right? So. Okay, so we have that, right? Hopefully that makes sense why that's the upper bound and that's the lower bound, right? Let's see, I need to figure out what my y values are varying between, so I have to figure out for myself what's the lowest the y value is going to be and what's the largest it's going to be. Okay, so I really need these intersection points here. Okay, problem says calculator's okay, right? So we'll just kind of use that, and actually, what does that tell us? We're going to write this out, and how about, whenever you have a calculator okay problem, you still need to show some math to get there. You can't just have a graph for it. AP doesn't like that. So I'm going to take x equals, and I'm going to plug I'm going to plug that in there. I don't want to solve both for x or both for y. I'm going to just do that. So at this point, you just show AP that you did that, and then you say, okay, here are my x values, and that's when you go to your calculator and you have your calculator do it. Even if you're doing your calculator, you don't have to plug this in. You can plug the two graphs in and then see where the intersections are. But AP is really picky. They want to see that equation exactly as it looks right there. So that's just, I don't know. That's just the AP being the AP, right? Right, for what it's worth. Okay. Okay, so I have that equation. All right, I'm going to use the solver. I'm going to plug. For me, this is how I would choose to do it. This is x to the 6th. I would move this x over. I would put that equation into my graphing utility. All right, my graphing calculator. Okay, I'd graph that equation there, and then look for the zeros, right, on my calculate right? So I have it in my calculator from 1995 calculator, still works, it's great, right? I'm going to find my zeros, right? And so I have the graph right there, and I'm going to get close as I can, right, for it. And I think the newer ones are better than mine, but, you know, this is what I have and it still works. So I got -1, yay. So the x is -1, and then we figured out that other one, and so I can calculate that other intersection. Right, you move over. As I said, maybe yours is better than mine in terms of its efficiency. Hopefully it's better because yours is 25 years newer than mine. So it should be better. And it gives me 1.24. I'm sorry, 1.215 when I round it. Okay, so those are my x values. They're not the y values. Okay, so I'll figure out what those y values are by plugging them in. And I can plug them into either one that I want there for myself. And so those are my x values, so the y's are going to be equal to, well, plug in right there, -1 for that. And then I'll take that 1.215 cubit, and that'll give me my second one of 1.794. Okay, so I have my two bounds there, right? -1, right? There's the lowest of -1, and there's my highest of 1.794. Okay. Okay, so now we're ready to integrate it. It says calculator okay. We just go and plug that into our calculator here. All right, there's no need to actually do the integration. Remember that the AP, when they say calculator okay, they're expecting you to use the calculator to do the integration. So that is one of the things, one of the expectations that they have. You're going to get no credit if you integrate correctly, because they're expecting you to not actually integrate, just to put in your calculator. So that's what I'm doing. 1.794. Okay. Calculator's thinking. Hopefully yours is faster. 25 years newer technology. Come on, wait for it. Wait for it. Still waiting. Still waiting. Bueller. Okay, it's still going. Oh, it finally gave me an answer of about 4.215. Okay, there we go. And that seems reasonable looking at what my graph looks like. Right? I could say to myself, yeah, that seems like it will work, right, for me. Okay, so there's example 1. If we're looking at example 2 here, okay, example 2, we have the same option as we're doing this, right? We have y equals the ln of x and y equals 5 minus x. Okay, we're looking what's in the first quadrant here. Okay, so find the area of the region. This one you didn't really have an option. You had to integrate across like this. This one you could choose. Do I want to integrate up and down, right, or do I want to integrate side to side? I'm going to do the side to side approach, so I can just set up one integral. If I do that side to side, I can see that the thickness is dy, and this is the change in x. Okay, for myself, right? So integrate. This is part A here, right? Let's see, it's going to go from 0 to whatever that intersection is. We'll figure that out in a second. And then the upper bound is y equals 5 minus x. So if I solve for x, that's going to be 5 minus y. I'll just move that over. Okay, so that's the upper bound. Okay, and if I solve this one, then I exponentiate both sides, and I get that it's e to the y, which is much easier to integrate than ln of x, although you can go right ahead and try to integrate that, right? If you want. If it's a calculator, okay, it's not a big deal, but this is a case where if you don't have a calculator, it's really a no-brainer. You want to use dy there. Okay, just need to find that intersection there. So we need to know when 5 minus x equals the ln of x for ourselves. Or actually, another way to think, I want to see if I can do this directly and have the y value stick around, but I don't think that's going to happen too well. Okay, this must be a calculator active, because just to find that intersection there, right, it's going to take a little time. So you write this out to show the AP what you intend to do. You go to your calculator and you actually find that intersection. I'm going to type in 5 minus x minus the ln of x. Okay, I'm going to graph that one, and then I'll find my zeros again. That's how I do it. That's what works well for me. Right, that'll tell me the x value So again, I'm moving everything over. I'm basically setting it equal to 0, and I graph the function, and then I look at the function to see where it equals 0. Okay, I have to get into the region there. I'm way out in left field. 1. I know some people prefer the calculate tool. Good for you. Do whatever works for you. It doesn't really matter. This graphing one really helps me, and especially when there's multiple answers, right? I prefer it, so that's why you see me using it. Okay, so we got the x value. That seems reasonable. 1, 2, 3, and change. I need to figure out that y value, so I'm going to take that and plug it in. Actually, probably easiest if I use the 5 minus x. So I'll just do 5 minus 3.157. And that's going to give me approximately 1.843. Okay, right on. There we go. We have our upper bound for the y value. Okay, we integrate that using our calculator, get an answer. I'm going to pause it real quick, do that integration just to see the answer. Okay, when I just integrated on my calculator, I got 2.201. Okay. Which seems reasonable looking at my graph. By the way, when I plugged it in, I don't know if you can see my calculator. There we go. Now you can see it, right? Older version, so this is a little different. But notice when I plug the equation in, I just change the x's to y's. No big deal, right? It doesn't matter what variable it is. It just matters that these are all the same variable when you set it up. So in the calculator, you just change it over, and you get your area there answer. Okay. You're skipping B for now. We're coming back to that, right? That's what you're doing next week with Mr. Warner. Okay. So let's take a look at at C here. Okay, so as we look at C here, you can see it's saying find the horizontal line y equals k. So there's going to be some horizontal, right? So some horizontal line. Okay, that divides this region into 2 regions of equal area. So this is an actual AP question. I remember seeing this and doing this before when I used to teach AP. So this is not something that's just come out of left field. This is something that they have asked multiple times in the on the open response section. Okay, so let's think about this, how we're going to set this up. Okay, so if we're looking at this, we want this region underneath to be equal to the area of the region above it. Okay, so really the way we set this up with the slices going sideways, that works perfectly here. So what do we really need? We need the integral from 0 to k of 5 minus y minus e to the y dy to equal k to 1.843 5 minus y minus e to the y dy. Okay, and if we look at that right, but do not solve an equation involving one or more integrals whose solution gives the value of k, hey, that would give us the value of k right there. We don't actually need to finish that problem off. That's all done there, right? So we're just by thinking about it as a horizontal line, we can just think of that's the upper bound, right, for this region, and this k is the lower bound for that region. And then if we actually integrate it, we find that answer. Hope that makes sense.